In this lesson, we are going to learn about calorimetry, which uses a device called a calorimeter in which the heat associated with a specific process is measured. There are two basic types of calorimeters. There is a constant pressure calorimeter, also known as a simple calorimeter or a coffee cup calorimeter, and there is a constant volume calorimeter, which is also known as a bomb calorimeter. In the first part of this lesson, we will look at simple calorimeters, and we'll finish the lesson talking about bomb calorimeters. The picture on the right denotes a constant pressure calorimeter. It got its name as a coffee cup calorimeter because of the fact that it can be constructed with two styrofoam cups, one nestled inside of the other, filled with some water. It is used to measure the heat absorbed or released by a process or reaction taking place at a constant pressure. For example, the heat of acid-base neutralizations or the heat associated with dissolving a salt in water can be measured. A constant pressure calorimeter can be constructed using two styrofoam cups, which is why it's also called a coffee cup calorimeter. A coffee cup calorimeter can be considered an isolated system. If an exothermic process occurs, the heat released by the reaction will be absorbed by the water and by the calorimeter, and you'll notice an increase in temperature by the thermometer. If an endothermic process takes place, heat will be absorbed from the water and from the calorimeter, and the temperature measured on the thermometer inside will decrease. Recall from the first law of thermodynamics that Q of the system is equal to negative Q of the surroundings. That means that energy is not created nor destroyed, but simply transferred from one system to another. For a process in a simple calorimeter, recall that the water and the calorimeter can absorb or release the heat. Therefore, we can rewrite it as Q of the reaction is equal to negative Q of the calorimeter and Q of the water. However, also recall that in a simple or coffee cup calorimeter, it can be constructed using styrofoam. Styrofoam is a very poor conductor of heat, which is why it's used as a coffee cup, and therefore it's often so small that it can be considered negligible. Therefore, we can get rid of Q of the calorimeter and simply write it as Q of the reaction is equal to negative Q of water. Then we will change negative Q of water to negative MC delta T. And this is the process that we'll always use for simple calorimeters. For example, burning methanol in an alcohol burner, which acts like a simple calorimeter, warms 426 grams of water by 14 degrees Celsius. Calculate the heat associated with this reaction. Well, as soon as we identify that this is a simple calorimeter, we can set up the first law of thermodynamics. This means that we can write Q of the system is equal to negative Q of the surroundings, and for a simple calorimeter, those surroundings will be water unless otherwise specified, which is equal to negative MC delta T of the water. We were told in the question that the mass of the water is 426 grams. We know from our data table that the specific heat capacity of water is 4.184 joules per gram degree Celsius, and we were told that it was heated by 14 degrees Celsius, giving an answer to three significant figures of negative 2.50 times 10 to the 4 joules. Example number 2 states that 4 grams of calcium chloride is dissolved in 100 grams of water in a simple calorimeter. As soon as we see that this is taking place in a simple calorimeter, we can set up the question. So Q of the system equals negative Q of the surroundings. For a simple calorimeter, the surroundings is water, and that's equal to negative MC delta T. Before the calcium chloride was dissolved, the water's temperature was 22 degrees Celsius. When it was all dissolved, the water's final temperature was 24.2 degrees Celsius. What is the heat of solution for this process? Well, the question is asking for heat of solution, which means it's asking for Q. The one thing that makes example number 2 different is the fact that the calcium chloride is dissolved in the 100 grams of water, and therefore becomes part of our surroundings. So, for a process where the reactants dissolve, the mass of the surroundings is the total mass of the solution. So in this case, we will not be using just the 100 grams of water, but we'll be using 104 grams of the surroundings. However, we will also assume that the solution is dilute enough so that we can still use the specific heat capacity of water. Therefore, Q of the system is equal to negative 104 grams times 4.184 joules per gram degree Celsius times TF minus TI, which is 24.2 degrees Celsius minus 22 degrees Celsius. Notice that I went ahead and subtracted those temperatures first to see if there was a change in my significant figures, and 24.2 subtract 22 degrees Celsius is 2.2 degrees Celsius, which does change my significant figures down to 2. So my answer is negative 9.6 times 10 to the 2 joules. So in this example, the takeaway is to remember that when things dissolve or mix, the reactants, the mass of the surroundings is the total mass of the solution, but we can still assume that it's dilute enough to take the specific heat capacity of water alone. Example 3 says 10 grams of metal X at 280 degrees Celsius is dropped into 200 milliliters of water at 20 degrees Celsius in a coffee cup calorimeter. As soon as we see that we have a coffee cup or simple calorimeter, we can set up the question. However, example number 3 is different yet again. We are told that we have 10 grams of metal X at 280 degrees Celsius that's dropped in 200 mils of water at 20 degrees Celsius. That metal X and water reach thermal equilibrium at 25 degrees Celsius, and we've been asked to calculate the specific heat capacity of X, which is C. This means that when I set up the question, I cannot simply leave it as Q of the system equals negative MC delta T, as I'm not solving for Q, I'm solving for C within that. Therefore, I'm also going to make the left-hand side of the equal sign equal to MC delta T. We just need to remember that the MC delta T here is for metal X, and the MC delta T over here is for water. Now we can plug in what we know for each side. In this case, we were told that we had 10 grams of metal X. We're looking for the specific heat capacity of metal X, and the delta T is 25 degrees Celsius, which is the thermal equilibrium reached, minus its initial temperature, which was 280 degrees before it was dropped into the water. That's equal to negative MC delta T for water. We were told that we had 200 milliliters of water, which is 200 grams of water, with a specific heat capacity of 4.184 joules per gram degree Celsius, and a delta T of 25 minus 20 degrees Celsius. At this point, this becomes a mathematical algebraic equation, which is individual. However many steps it takes for you to solve for C is fine. Therefore, I'm just going to show the final answer. And the final answer to the appropriate number of significant figures is 1.6 joules per gram degree Celsius. The last example we'll look at for simpler coffee cup calorimeters is example number 4. Consider the following neutralization reaction. When 50 ml of 1 molar hydrochloric acid and 50 ml of 1 molar sodium hydroxide are mixed in a coffee cup calorimeter, the temperature of the resulting solution increased from 21 to 27.5 degrees Celsius. What is the heat of reaction measured in kilojoules per mole? The fact that they're asking us for units of kilojoules per mole means in this question they're asking us for delta H. Since this is in a coffee cup calorimeter, Q of the system is equal to negative Q of the surroundings, which is equal to negative Q of water and negative MC delta T. The only problem with this question is the fact that there's nothing quoted about water. However, remember that we are looking at a neutralization reaction between an acid and a base, and an acid and a base will completely neutralize in order to give us water. So the fact that we had 50 ml of hydrochloric acid completely react with 50 ml of sodium hydroxide means that we are going to have 100 ml of water. So the mass of the surroundings would be the mass of sodium hydroxide and the mass of hydrochloric acid. However, we're still going to assume that the solution is dilute and completely converted to water, and the fact that the salt is present, it's still dilute enough to use the specific heat capacity of water. Plugging in what we know, negative MC delta T is now equal to negative 100 grams of water times 4.184 joules per gram degree Celsius times a temperature change of 27.5 degrees minus 21 degrees Celsius. Given the fact that this subtracts to give us 6.5 degrees Celsius, I have to have an answer to two significant figures. In this case, grams cancels, degrees Celsius cancels to leave an answer in joules. However, recall the question asked for the answer in kilojoules per mole, so I'll divide that by 1,000 to get negative 2.7 kilojoules. Now I have to work out the number of moles. Recall that the question asked what is the heat of this reaction measured in kilojoules per mole of hydrochloric acid. Therefore, I need to find the number of moles of hydrochloric acid. We are told both the concentration and the volume of HCl, so we're going to use number of moles equals C times V. We were told that we had a 1 molar solution of hydrochloric acid and that we had 50 mils of that. We must convert that to liters before we can multiply to give us the number of moles of 0.050. I can finally solve for delta H. Recall that delta H is equal to Q divided by N. I found Q to be negative 2.7 kilojoules and the moles to be 0.050 to give me an answer to two significant figures of negative 54 kilojoules per mole. The second type of calorimeter is a constant volume calorimeter, which is also known as a bomb calorimeter. It got a nickname of a bomb calorimeter because it's used to measure the heat released by combustion reactions that's taking place at constant volume. A bomb calorimeter consists of several basic components. First, a bomb calorimeter is specifically manufactured and bought. It cannot be made with simple materials. It has a small chamber inside of the bomb calorimeter that is surrounded by a constant volume of water. Inside this chamber, you can put your sample that's in a cup that can hold it, as well as an oxygen inlet in order for the combustion reaction to take place, and some wires that are in contact with the sample that can be ignited to cause the combustion reaction to happen. There's a stir rod that consistently stirs the water so we have a uniform solution, and a thermometer that can take the temperature. Since this is a calorimeter, we still apply the first law of thermodynamics that says Q of the system is equal to negative Q of the surroundings. For a process in a bomb calorimeter, the system will always be the chemical reaction, and the surroundings in our case is both the calorimeter, the walls of the calorimeter, and water. Unlike a simple calorimeter, the walls of a bomb calorimeter are made of a metal, so the walls will absorb the heat that is released by the combustion reaction, and therefore we cannot consider it to be negligible. However, since bomb calorimeters are specifically manufactured for a constant volume of water, they're normally calibrated for that constant mass of water, and it's included in the heat capacity that is supplied by the manufacturer. Therefore, for a bomb calorimeter, Q of the system is equal to negative Q of the calorimeter, which will change to negative C delta T, since the heat capacity is supplied by the manufacturer. For example, a 1 gram sample of sucrose is burned in a bomb calorimeter. As soon as we see that it's burned in a bomb calorimeter, we can set up the question. For a bomb calorimeter, Q of the system equals negative Q of the surroundings, which equals negative Q of the calorimeter, which is equal to negative C delta T. We were told in the question that it's burned in a bomb calorimeter with a heat capacity of 7 kilojoules per degree Celsius, and that the temperature change goes from 25 degrees Celsius to 27.3 degrees Celsius. Plugging this into our formula, we get a Q of negative 16 kilojoules. In addition, the question also asked us for the molar enthalpy of combustion, which is delta H. This means that we now have to solve delta H, which is equal to Q divided by N. We can solve for the number of moles off to the side. Since in this question the combustion reaction is taking place for the sample of sucrose, we have to find the number of moles of sucrose. We were told that we had a 10 gram sample of sucrose, and we were given the formula to help us solve for the molar mass. This gives us 0.00292 moles. Plugging both the Q and the moles into delta H is equal to Q divided by N gives us an answer of negative 5.5 times 10 to the 3 kilojoules per mole. I now strongly encourage that you continue on and attempt thermochemistry worksheet number 7.